Okay, we have two different kinds of yields. We have the actual yield, which is based on how much you can actually measure. How much did you get out of this reaction? You put it on a scale, you measured it. And then the theoretical yield. And that is how much we get based on all the mole ratios that we've done before. So everything we've done in this whole chapter so far, all lessons 1, 2, and 3 in the quiz you did yesterday, those are all theoretical yields. They are your prediction for how much you should make out of two things. It's like, I reacted this many grams of iron, how much iron oxide can I get? And that's a theoretical yield. So for us, we are going to do now, those don't always agree. We figured that out in our masses of iron and copper lab that we did, where we put the nail in the copper chloride solution, and then we measured how much we made. And it wasn't perfect. It was a little off. And so now we're going to find the tools that we can do a percent with that. And so the percent yield is a very simple calculation. So we're going percent yield, percent yield is equal to actual divided by theoretical. And then we times by 100 to make it a percent. That's the whole calculation. It's why is there a difference between what I actually measured and what I actually think I should get. When I did math, I get a number. When I did an experiment, I get a different number. They're not the same, so why is basically the questions. There are some good reasons why. Some of them are the reaction was not complete. So the reaction was not complete. In other words, basically, it didn't finish it. Like, sometimes reactions, which we'll get to later, need a certain level of heat to keep going. They need to be warm, in other words, to keep going. If they're too cool, they kind of stop reacting, right? You need to heat stuff up before it reacts. So if it didn't get all that way through, it might not have finished. There might be a side reaction happening. Might happen. Now this is once I've made something, that something started reacting with something else in the environment or in the beaker or whatever we're measuring in, and it started to turn into something else that we couldn't measure. And so when we measured what we thought we made, it had already started turning into something else. And so how much is less than what we expected? We could also have some like physical loss of the substances. Physical loss or impurity. So it might have other stuff stuck to it and kind of collecting around it, or it could have like physically been lost to like a vapor, like if you're capturing a gas, some of it can leak out and so on. So there can be physical loss or impurity. Or what we will get to, and you will love the most, equilibrium reactions. Ask your friends who have finished Chemistry 12 how much they like equilibrium reactions and see how that goes. So equilibrium reactions, in a quick spoiler, is that some reactions work backwards and forwards. So if you make two things, those things react to make the things you started. So they kind of can go back and forth. Some reactions are like that. And so you might not get all the way to one reaction. It might start turning back into what you started with. So some reactions do exist like that. So those are basically the fun reasons why you might not get 100% of your expected amount. Now, fun in chemistry, as opposed to physics class, you can record accurately a percent yield that's more than 100%. So you can measure the weight of something more than what you think you should get. That is usually due to this impurity chunk in it. This happened with our copper solution that we were measuring in the previous lab, the moles of iron and copper lab, where we do the nails and the stuff. You got a more than you expected, probably because what you measured as a mass had other things stuck to it. It wasn't pure, and so there were extra things stuck to it, and therefore you measured weight that wasn't supposed to be measured, and so your measurement was 1% over 100, even though we know that's not theoretically possible. But it still can be a true measurement, and we can work with that. That's part of your experimental error, is that like there was a bunch of impurity, a bunch of other junk in it. That's why I measured a heavier mass than expected, which is fine. Okay, so we're going to do a few calculations here. We're going to see some theoretical yields from before, and then we're going to put some actual yields and percents on top of it. So we're going to do some butane reaction. So we got 80 grams of butane, and we had a whole bunch of oxygen, so more than enough oxygen, which usually comes from the air, so we don't measure it. Then we do 117 grams of water are produced. So step one is balance the reaction. I'm going to look at my carbons and my hydrogens. It might always check us. It's like, I'm looking at my hydrogens here. What's half a 10? 5. Is 5 an even number? No. So what I'm going to do is I'm going to go 2 out front. I know that's going to show up and say 2 out front. Therefore, I need 10 of those. I need 8 of those. And now my total number of oxygens are 10 plus 16 is 26. Take that in half, we get 13 as the number over here. So this is my balanced reaction for butane. It's a combustion reaction, burning of butane. Butane is used in lighters, like just either like the barbecue lighters or the little flick lighters, wherever you need. Those are butane, the chemical. That's what we're there for. So let's calculate the theoretical yield of water. So what we're going to do is we're going to start with what we started with, the butane. If we burned that much butane, how much water should we get? So the theoretical yield starting with the butane. So using all the percents that we've done all along, we're starting with 80.0 grams of the butane, and we're going to multiply it by my grams per mole, upside down because that's how the concentration works. But we need to find out what the molar mass of butane is. Okay, 4 carbons, 4 times 12 is 48, and I have 10 hydrogens, so it's 58. The adding isn't bad. So it's 58 grams per mole of the butane, C4H10. So that's the butane. And then we got to do our mole ratios here. So we're going to go mole butane. And I want water, mole H2O. So then we put whatever numbers are in front of it on the chemical reactions. And even if they do simplify, I think it's perfectly the correct choice to put the real numbers on, even if they would simplify. So water is 10. Water has a 10 in front of it, and the butane has a 2 in front of it. So I'm still going to write 10 and 2, even though I know it simplifies to 5 and 1. I know that I'll write 10 and 2 because it matches, and I can see that this 10 is what goes here, and this 2 is coming from there. It's just a visual thing. When you put it in your calculator, it'll disappear like it knows to. And I want to figure out how many grams of water I'm going to make. So I've got to turn this back into grams per mole of water. Water is 18 grams per mole. Some of these compounds we use over and over so many times. Like, you're going to get to, like, memorizing some of these masses. Like, water is 18 and so on. Then we can get a number out of this. We can get our calculators out and get numbering. Back to on. 124.1379. It's a lot numbers, so just a bunch of numbers. That's way too many. How many real numbers should I keep? Just the 3, so it's 124 grams water. So that's how much I should keep. That's the finished answer to part A. What is the actual yield of water in this reaction? Here, let me slide this up so everyone can see. There we go. What's the actual yield of water? Yeah, so boringly, actual yield is oops, wrong color, 117 grams H2O. Because it's just given in the question. It's very exciting, right? It's just that number, and that number. They're just the same. So now we get to do our percent yield. So we will percent yield it up. And I get to be lazy and write percent yield like this. And you will often see it like this because scientists in general are lazy. And so instead of writing P-E-R-C-E-N-T, we'll write percent symbol because we're lazy. I'm so proud I said that, spelled it right out loud the first try. Okay, so it's actual divided by theoretical, theoretical, I'll spell it right. Actual yield is 117 grams, divided it by 124 grams, and then we'll multiply it by 100%. Let's see what I get. 117 divided by 4, 0. Nope, so I want to times it. So I'm getting all the way to the right spot. Times 100 equals 94.4. So in this particular reaction, in this particular experiment, we get 94.4% of the water that we expected, which is pretty good, I think. You get 94%. Now, in certain labs over many years, I've done for many times, I have gotten some very ridiculous percent yields over time. Like, I'm getting like 7% yields or like 180% yields. I've gotten some really ridiculous things. When you're actually physically pouring, weighing, and measuring chemicals, it's very hard to be super accurate. All right, guys, so I want you to try part A entirely on your own because you absolutely can do it, and you were totally tested on this yesterday, so this is where we are expecting you to be. So do your balancing of the reaction. It's a propane reaction. You should already know how to balance this. And then you do your moles to, or mass to moles to mass. Can get your mass out. And then we'll do the rearrangement of the percent formula after. Recording. There, we've done that, hopefully, tried it, checked everything. I will do the actual yield part. So we have our percent equals A yield over T yield. I'm getting really lazy with my percent now. That's actual yield and theoretical yield. Just to shorthands. Okay. Yeah, there we go. That works. Okay, so I want this thing. So that's just unnecessary. We can just deal with that first. Because I can do this. It looks like theoretical yield is 28.05 times 0.70. Just turn it into a decimal to do math on it. I don't know. I probably should still go back to do it 3. I should probably say it's 19.6. There we go. Okay. Okay. Pause. Stop. For the next one, I'm going to set up, make sure some of you have already done it, but we got to make sure we get our formula reaction right. So we're going to do wrong colors. Colors here, Cl2 plus Al all by itself because aluminum is a single, forever aluminum, and we have AlCl3 for aluminum chloride. So aluminum chloride is an Al3 or AlCl3 because it's a 3 plus with a 1 minus ion, and so they balance like AlCl3. Now I got to balance this. The balancing steps is a 2Z, 3Z, and that makes 2 here. So now my reaction is balanced. So now we're here at a reaction that's balanced. We can now do all the steps that we learned in the last units to figure out the new mass. So I want to get theoretical yield of aluminum chloride. So I am doing this pair. I'm matching these two things together. I'm taking my chlorine measurement and I'm turning it into aluminum chloride measurement. Most of you have already done it that were ahead of me and think that they could do it, so I'm going to just talk through this one for those that didn't get through the first one. So just follow along if you've already done it, and you can check your answers. Hopefully everything's above board. Start with what we're given. 80.0 grams of Cl2. We're going to multiply it by... Now we have to be careful. Chlorine is 35.5, but this is a Cl2. So this is 71.0 grams per 1 mole of the Cl2. Chlorine gas is a pair, so you have to put both of those masses together. Next step is the mole ratio step. We're going to do moles of chlorine, so it's 3 mole Cl2, and we're going to aluminum chloride, so that's 2, what's that happening? Mole AlCl3. So now that we've done our mole ratio step, we can turn it back into a mass step. 1 mole AlCl3, and I got to do the molar mass of aluminum chloride 3. So I got to get 35.5 times 3 plus aluminum's 27. So I get 133 and a half. 133.5 G. And now we can do our math. I'm going to get it all the way down the bottom because I've written too big. So get to the calculator. 80 divided by 71 times 2 divided by 3 times 133.5. I get 128, 16, so a lot of numbers. 100.2816. Bunch of numbers. That's too many already. We're going to have to round this to 3 significant digits. Ew. 100 grams of, oops, I don't want grams. Don't need to write like that. AlCl3. Or alternatively, if you want to be really good, 1.00 times 10 to the 2 grams is also a good way of writing that. That is mean. I should fix that next time. But it's still true. So we want 3 significant digits for the number 100, which is a pain. But that's how we set it up. So, yeah. Good news is that we're doing the same actual yield that we did in the previous steps. So the formula is exactly the way it was up above. So I can go straight into actual yield is going to be the theoretical yield times the percent number as a decimal. And we will write that in. Theoretical yield is 100, but I'm going to use more decimals, 0.2817. And then multiply that by the percent, which is 0.642, to give myself a whole bunch of extra decimals. So just take the number that I didn't even take out of my calculator. I've got all like 17 decimals still stuck in my calculator, and then multiply that by 0.642 and see what I get. 64.4 in 3 different digits. So 64.4 grams of ACL3. Oops, AlCl3. There we go. Dots. Done. Stop. All right, I looked it up. I now have some questions for us to work on for the rest of the day. You can now do a few more of your formal assignment because now you know how percents work. All done.